In the 1st century AD, Flavius Josephus found himself and 40 other soldiers trapped in a cave by Roman soldiers. Rather than surrendering, they decided to execute themselves one by one. To do this, they formed a circle, started with one person who would execute the kth person to his left until there was only one person remaining who would just execute himself. Josephus, deciding he'd rather surrender, needed to quickly figure out which position he should stand to be the last person remaining so that he could just surrender. This is a very famous computer science and mathematics problem called the Josephus Permutation, to try to calculate where the last position is given the number of soldiers and the integer k. But instead of just finding the last position, in this video, I think it would be interesting to generate a list of the order in which each soldier gets executed, where Josephus' position would be at the very end. So we need to create a Python function that can take in a list of integers, which will just represent the indices of where each soldier is standing in the circle. It should also take in an integer k. The function must extract every kth item from the list cyclically to form a permutation. In other words, let's say we have an input of 7 soldiers and k is equal to 3. Starting at index 0, to get to the 3rd item of the list, we only need to move over twice, or k minus 1 times. We remove 3 from the list and add it to our permutation. Once 3 is removed from the list, we're still at the same index, but now it contains item number 4. So from here, to get the next 3rd item, we move over k minus 1 times to get to 6. Then we remove it from the list. Once we reach the end of the list, we should continue back at the beginning of the list, removing each remaining 3rd item. And at the end, we should have a permutation, which is what should be returned from the function. Okay, so to start, I'm going to create a function named solution that takes in array and k as inputs. Next, I want to create an empty list for our permutation, which is what will be returned at the end. Now I want to keep track of our index as we iterate through our array, so starting out, we start at index 0. Alright, so now we want to iterate through array until we've removed every item from array and put it into our permutation list. So I'll create a while loop here saying while array. Once array becomes empty, it becomes a falsy value, and so this while loop will end. All right, so in here, in order to get the next kth item, remember we needed to move over k minus 1 times. So here, I want to increment our current index by k minus 1. So I'll do index is equal to index plus k minus 1. Once we're at the kth item in the array, we want to pop it, so we'll do item is equal to array.pop at that index. Then we can append that item to our permutation. And that's all for the while loop. We can just return the permutation out here once the while loop completes. Alright, but now we have one major problem here. In this while loop, we increment our index by k minus 1 every iteration. Well, what happens when we reach the end of the list? We need a way to circle back to the beginning of the list once we reach the end. To resolve this, all we need to do is modulo this with the length of the list. Once our index is equal to or exceeds the length of the list, this operation becomes important. For example, if we're currently at index 4 and we need to move over k minus 1 times, we would increment our index by 2 in this example, which would be at index 6. But we can't actually get to this index because it doesn't exist. So if we do 6 modulo 5, which is the current length of the list, we would get 1 here because it's the remainder of 6 divided by 5. So our new index has circled back to 1. All right, so let's test our solution. So to start, let's say we have 7 soldiers. Now to create our input array, let's use list comprehension to say s plus 1 for s in range soldiers. Then let's set k equal to 3. Alright, so we'll set perm equal to solution with our array and k as inputs. And then we'll print perm down here. So let's run this. And yeah, looks like we got the correct permutation. Alright, but now let's really have some fun with it. Let's see how well our function performs with 1 million soldiers. I want to see how long this takes. So I'll import time up here, and before the function call, let's say start is equal to time.perfCounter. And then after the function is complete, let's say stop is equal to time.perfCounter. And then let's print stop minus start here. Alright, so let's run that. All right, so that took 224 seconds to complete, which is just terrible. If we take a look at our solution, you'll notice that we're popping items from the middle of our array each loop iteration. This is where a lot of time is spent in our function. You see, when you pop an item from the middle of the list, each item after it has to be shifted up to fill its place, meaning this has a big O of n time complexity. And if you're doing that in a while loop for each element of the array, it expands that time complexity to a big O of n squared. But I think I might just have a solution to this problem. You see, instead of having our array being a list, let's convert it to a deck instead. Now, a deck, short for double-ended queue, is another data structure similar to a list, and it can be imported from the collections module. Okay, so what is a deck and why should we use it here over a list? So first, let me explain how lists are stored in memory. When you create a list in Python, the pointers of each element of the list take up neighboring addresses in memory. This allows for one of the greatest advantages of lists, indexing. You see, if you needed to get the element in the 4th index of this list, Python knows where the 0th index is and can just perform a calculation to know exactly which address in memory it needs to jump to get to the 4th index. It doesn't have to step through each index until it reaches the 4th index. This, of course, comes with its drawbacks. When I remove an element from the list, in order for the list to keep its indexing feature, it needs to shift all subsequent elements that come after it, which, as I stated earlier, is a big O of n operation. The elements of a deck, on the other hand, are not stored in neighboring memory locations. Instead, the elements are connected by pointers, and it keeps track of the head and the tail of the deck. So if we wanted to remove 9 from this deck, we can't simply index to the 9 like we did with lists. Instead, we need to rotate the head of the deck until we get to the 9. To do this, we'll need to perform a rotate of -3 until the 9 is at the head of the deck. Now note, we're not moving any of the elements in memory, we're just adjusting the position of the head. Okay, now once 9 is at the head of the deck, we can perform a pop left on our deck and it will remove the 9. Now remember, at this point, a list object would have to shift every element after the 9 to fill its place. All decks have to do is just adjust their pointers. So this makes popping elements from a deck a big O of 1 operation, which is much more efficient. Okay, so back to our solution, let's convert this array to a deck. So let's say D is equal to deck with array as the input. Now we no longer need to keep up with an index, so we can remove this. And in our while loop, instead of calculating an index here, let's just rotate our deck 1 minus k times. This will rotate the deck until our kth item is at the head. And once our kth item is at the head, we can do d.popLeft to remove it and store it in this item variable. And then same as before, we'll append that item to the permutation. All right, so with that, let's run our solution again to see if it's improved any. So let's run this. And there we go. That's way faster than the 200 seconds we got earlier. And just to prove that we're still getting the correct permutation, let's set the number of soldiers back to 7 and just print perm down here. And when we run this, you'll see that, yeah, this solution still gives us the correct permutation. This was a pretty fun problem to solve. It's definitely helped me be more aware of the many other data structures available and how each of them can be utilized according to their strengths. Big thanks to the Byte Club members for your continued support. It's very much appreciated. If you enjoyed this video, be sure to leave a like, and the best way to see more content like this is by hitting that subscribe button and turning on notifications. Thanks for watching, and I'll see you all in the next video.